Hello, physics students. Welcome back to my class. First, answer this question. The answer is 4, displacement. All you really need to know from previous lessons is that velocity is displacement over time. So once we have that idea, we're going to watch a video.
Top speed. That'll always be a marker of engineering achievement. But for the stretches of pavement most of us see on a regular basis, those numbers hold little to no relevance. Acceleration, on the other hand, is a much more useful and accessible metric by which to experience how a vehicle moves through space, and it's something that few cars are truly masters of. Welcome to the 2-Second Club. The 6th generation Nissan GT-R is the company's most capable street car ever, and by far the least expensive example in this test. But money isn't everything, as Nissan shows, for it was the quickest out of the hole and up to 45 miles per hour.
There's a lot of fancy numbers and stuff going on in this video, but here's the key idea. This car went from 0 to 60 miles an hour in 2.94 seconds. Under 3 seconds, but about 3 seconds. That's why it's in the 2-Second Club.
The 911 Turbo S is the absolute quickest road-going Porsche the world has seen, and the contender that came closest to dethroning the almighty Bugatti Veyron. As of today, it still holds the vice presidential seat, and is poised to step up at any time.
Okay, that's enough this video. This is the important number right here. The cars go from 0 to 60 miles an hour in under 3 seconds, but about 3 seconds to the first one. So that's what we're going to look at today. This is a really important idea for this first unit in physics. The most important idea, it's acceleration. It doesn't really matter that a car can go really fast. If you go watch a car commercial or go to a car dealership, which I'm sure you guys don't, but if you did, they wouldn't say, hey, this car can go 160 miles an hour, 180 miles an hour, 200 miles an hour. That might be true, but you're never going to drive that fast in real life. That's not really relevant to most driving. Most people, when they talk about how fast a car goes, they say, oh, the car goes from 0 to 60 miles an hour. And let's use SI units. That's about 0 to 27 meters per second. These cars, they took about 3 seconds. That describes the car's acceleration. Acceleration is described as a rate. Rate is an interesting word. You guys may have heard the term rate in math. I would say in physics, we use it a lot. I would describe velocity as a rate, speed at a rate, and therefore acceleration is also a rate. So how can we define a rate? There's lots of possible ways, so you try it, I'll tell you what I think. How do you define rate? In physics, rate implies a rate or how fast something changes per time, the rate of change per time. It's a change over time. If I go from 0 to 27, 0 meters per second is my initial velocity. V subscript 0 or V naught stands for initial velocity. And then any velocity after that, just call it V, velocity. If I went from 0 to 27, the change in velocity is 27 minus 0, V minus V naught. That's the amount my speed changed. But that's not really relevant. Any car, if it's like drivable, can pretty much get to 60 miles an hour. What we care about is how fast they do it. If a car is really, really powerful, a really nice sports car with a really strong engine, it can go from 0 to 60 really, really quickly in a very short time. So we care about the change per time. It's a rate of change with respect to time. It's also very common to see this drawn or written with delta. Delta means change. Delta is like kind of like difference. It's like a D in Greek, a change, a difference in velocity over time. These are equivalent formulas. The rate of change of velocity in time is your acceleration. So, very straightforward example. For the first car in the video, it went from about 27 meters per second to 0 meters per second. Note that you switch the order. It's not initial minus final, it's final minus initial. 27 minus 0 meters per second over 3 seconds. The acceleration was about 9 meters per second per second. Very strange units, 9 meters per second, and they can actually be explained another way. 9 meters per second squared. So every 1 second, the car was going 9 meters per second faster. When it started out, it was going 0 meters per second. There was a rest. After 1 second, it was going 9 meters per second. After 2 seconds, it was going 18 meters per second. After 3 seconds, it was going 27 meters per second. And if it kept the same acceleration for another 1 second, it would, in theory, be going 36 meters per second. In real life, things don't have constant acceleration for a long time. Cars don't work that way. But we're going to assume they do. We're going to assume for this whole unit that acceleration is constant. A constant acceleration of 9 meters per second, that's the change in speed, every second, that's the time it takes to change speed that much. But another way that we'll use to describe it is 9 meters per second squared. So, there we go. That's a pretty good rough definition of acceleration. This is going to come up later, so I'll show you guys one more time. So I'll show it to you really fast, but we're going to move on from there. Imagine a graph of velocity versus time. How would this graph look for the car, the first car in the video that started at 0 and went up to 60? Basically, the driver got the car and pressed the gas as hard as possible. So what would this graph look like? Tell me right now. If the car started at 0 meters per second, then went up to some higher number, say 27 meters per second, it would have taken some time. So we would, in theory, get a nice straight line graph. It's 27 meters per second. Is that too small for you guys to see? Sorry. In 3 seconds. If you look at this and use your brain, you might realize something we'll come back to next week. If this is true, and acceleration is the change in velocity over change in time, is the change in the y-axis over the change in the x-axis. It is the slope. Acceleration can be thought of as a slope of a velocity versus time graph. So this is another really important idea that you need to understand. An object can have velocity but no acceleration. Really, Mr. Lamb? Yeah, really, Sage. No, you're Hazel. An object can have velocity without accelerating. You don't need acceleration to have velocity. And the reverse is true too. You don't need velocity to have an acceleration. There could be some point in time where you have a velocity, but no acceleration. We'll talk about that pretty soon. How would that look? What would that be like? How would we see that? I'm not going to ask you guys to tell me. I'm just going to draw it out. What if the car is driving down the highway, they get up to 60 miles an hour, and then they say, this is pretty fast, this is fast enough, I'll just keep this same speed. I'll just keep driving down the highway at 27 meters per second. The slope of this line is 0. So the slope would be 0 meters per second squared. The units of acceleration are always meters per second squared. But the velocity is not 0. So the car is moving without accelerating. This is not a contradiction at all. You should definitely be able to understand. You can have velocity without acceleration. We'll talk about the reverse later when we have some more time, but that's a very important idea. You can have velocity without acceleration. You can have negative acceleration too. You can have deceleration. Let's say you're driving, I don't know, a little faster, 30 meters per second, and let's say you slow down to 10 meters per second. Let's say you get into some traffic. And let's say this happens over, I don't know, 2 seconds. It's pretty fast. You hit this traffic light, and it's just like, ooh, gotta slow down. Well, plug it in the formula. My velocity, it's easier to start with initial velocity because it's your initial. It's where you start. What was my initial velocity? It's not 10. I started out moving. This is a really important idea. Physics is not, never mind. In these problems, you don't always start from rest. Oftentimes you start moving because in life, things are often already moving. The Earth is already moving at, as we said, like 30,000 meters per second. So things can start out moving. That's not a problem at all. We started out at 30 meters per second. We go down to 10. So this is 10 minus 30 meters per second. I'm going to write the formula. A equals V minus V naught over T. 10 meters per second minus 30 meters per second over T is 2 seconds. Negative 10 meters per second squared. So you can have a negative acceleration when you're slowing down. That's known as deceleration. And to be specific, it's not just when you're slowing down. It's when your velocity and acceleration are in opposite directions. So here's an example. If I take my marker and I throw it up in the air, it leaves my hand at a pretty high speed. What happens to that speed as the marker rises? Does the marker speed up, slow down, or keep the same speed? The marker slows down. Wow, thanks Daisy, that's right. The marker slows down. The marker leaves my hand at its fastest speed. It goes up, it gets slower and slower and slower and slower and slower and slower. So its velocity is upward, but yes, our velocity is upward, and we will say upward is the positive direction because that just makes sense for this problem. The acceleration, if we found it, would be negative, so it would be downward. And in that case, the velocity is upward, the acceleration is downward, we will say it's decelerating. And in normal terms in English, it's slowing down, which is fine. Sometimes problems will say an object decelerates and give you a positive number for the acceleration. You might have to flip it in your mind. Sometimes the problem will not do that. You'll see examples where the wording will tell you what's the acceleration or deceleration. And if you're not sure, you can just ask me. It's okay. But we'll see some practice problems. If it says deceleration or slowing down, you know the acceleration should probably be a negative number if the velocity is positive, which just makes sense. Okay, so really important idea. We're going to move on from the definition of acceleration. Okay, So assuming our acceleration is constant, we can find a lot of interesting stuff. First, we're going to rearrange this formula for no reason. Solve it for v. We'll get v equals v naught plus a t. And this, they mean the same thing, but this is a little cleaner and it should make a little more sense kind of like intuitively. What's your velocity at any time? Well, it's wherever your velocity started plus the change in velocity, right? Your velocity at any time should be your initial velocity plus however much it changed. If I start at 5 meters per second and I go up to 20, well, I went from 5 to 20, I gained 15. So my 20 meters per second is 5 plus 15. That's just straightforward math. So that formula is fine. Let's do a quick little practice problem. Let's say my initial velocity of a certain mysterious car is 20 meters per second, and it accelerates at 1 meter per second squared for a time of 4 seconds. It's pretty obvious how to find the final velocity. Plug it in the formula. 20 meters per second plus 1 meter per second squared times 4 seconds, 24 meters per second. I kind of glossed over this, but this delta V is A times T, because A is delta V over T. I'll leave that for you guys in case you need to look at this more. So this is all fine. Here's a big question. How do you find the displacement of the car in those 4 seconds? It didn't start from rest. It started out going 20 meters per second. That's really important. But if we know physics and we know math, we can find how far it traveled. If we know how fast it started going, how much it sped up by, and how long it sped up for. So try and figure it out right now. How can we solve this problem? How can we find D? What do you guys think? If you have some ideas, tell me right now. All right, let's ask my babies what they think. Daisy, you think it's 80 meters per second? No, Mr. Lamb, it's not 80 meters per second. Why not? Is it more or less? It's more, because if the car was going 20 meters per second for 4 seconds, it would go 80 meters. But it wasn't going 20 meters per second for 4 seconds. It started at 20 meters per second and went faster. Oh wow, that's really smart, Daisy. So it's got to be more than 80 meters. That's right. We know it's more than 80 meters, but not much else. Any ideas, Hazel? It's got to be less than 96 meters. Why? Why less than 96? Well, a car going 24 meters per second for 4 seconds would go 96 meters. That's right. That's pretty good math for a baby. Yeah, but this car wasn't going 24 meters per second for 4 seconds. It started at 20 and only reached 24 meters per second at the very end. Oh yeah, that's right. So, D, the displacement, is between 80 and 96. I don't know. Sage, what should we do? Sage's brain is like pumping really hard. I'm thinking really hard. My brain's working. Oh, I know. Sage says, let's make a table. A table? Okay, if you say so, we'll make a table. Velocity and time. Technically, it's magnitude of velocity. Technically, I said velocity like 100 times this video. It was always magnitude of velocity because I never said a direction. So we started out at 0 meters per second. No, we didn't. Sorry, at 20 meters per second. when we started at 0 seconds. But there we went to 1 second, 2 seconds, 3 seconds, 4 seconds. We know we end up at 24 meters per second. That's my final speed. What should the speed be in each of these little intermediate steps? Well, our assumption is constant acceleration. So we should assume it's a nice smooth change. 21, 22, 23 meters per second all the way down. This is not exactly how cars usually behave in real life, but we're assuming it's true for now, and it's a good place to start. So, now Sage, what should we do? Oh, okay. Sage has this idea. Well, in 1 second, the car was going 20 meters per second, then 21, then 22, then 23. So maybe it's like 20 plus 21 plus 22 plus 23. Sage is like 86 meters or so. They said, how far does the car go in this time, this time, this time, this time? Close, but not quite. You can't say from 0 seconds to 1 second the car was going 20 meters per second or 21 meters per second. The car's speed is always changing. So you can't break down the time into sections and then find the distance the car went in each little section of time. Because there was no time that you ever know the speed precisely. The speed was always changing. The velocity is always changing because by definition, acceleration is change of velocity. So you can't make a little table. This is a really useful table. This is a great thing to do because it shows that you understand how the velocity changed. But you can't use a table and add up the distance the car went, the displacement of the car for each little increment of time because there was always changing velocity. So we have to go back to this assumption that we made last lesson that was actually wrong. Average velocity. I like the bar more than avg. Same thing. Average velocity is total displacement over total time. Really, total velocity would be a better term, but it's not always the biggest. So it's total displacement over total time. That's good. And we want to find total displacement. So this is a really useful formula. Well, the assumption we made before was that it is equal to the average of the velocities. This is v minus v naught over t. The average of the two would be v plus v naught over 2. Notice the differences, they're not the same. V minus v naught over t, v plus v naught over 2. Okay, guys. We assumed that this was true last lesson, and we got punished. It did not work out for us. It didn't work. But now we're assuming it's true, and actually it is. Under our new assumption that the acceleration is constant, this actually is true, and that's what we'll use to answer this question. It's kind of hard to explain why. So if you want, you can try to explain why. I don't expect you to be able to, but if we assume acceleration is constant, this does work. But in my previous example where I drove to school at 30 miles an hour and back 90 miles an hour, it did not work. If you can explain why, try right now. Okay, welcome back. So we are going to say this is true. So we're going to solve this weird formula for d. D equals v, this is kind of messy, but vt over 2 plus v naught t over 2. That's fine, but it's still kind of ugly. So algebra time, take this and plug it in here. This v we're replacing with this v. So now we got a big old algebraic thing. Why are we doing this? I said so, that's why. V naught t over 2 plus a t times t over 2 plus v naught t over 2. Pretty nice. D equals v naught t plus 1/2 a t squared. We got the most important equation of this lesson, and we got the same thing on the reference table equation sheet. Don't believe me? Scroll right on down to the second page. You'll see the first thing I wrote. V equals v naught plus at. There's some x's there that we're going to ignore for now. And we got the formula. D equals v naught t plus 1/2 at squared. You guys don't see it? It's this one right here. X equals x naught plus v naught t plus 1/2 at squared. Why are these x's and not d's? X is position. What does displacement mean in terms of position? Yeah, good job. Wow, that's Hazel, that's right. Displacement is a change in position. So a change is the value minus the initial value. So if you use x minus x naught and d, you will get x equals x naught plus v naught t plus 1/2 a t squared. That's on the equation sheet, but this is much nicer and neater, and it makes more sense. It'll help you solve more problems. Very few problems will tell you the car was going this far for this long, or the car was going this fast for this long and accelerated at this rate. Find where it ends up. Oh, also, by the way, it started at the 76 meter mark. That never happens. That's just like extra information. That just makes the problem more complicated. They'll ask you how far did it go from its starting point. They'll ask you the displacement. I said it. So, okay, I know I said that really fast. Like they wouldn't give you a whole problem and then say, oh, also the car started at 76 meters, so where did it end up? They'll say how far they'll just like, well, the car started somewhere. All we care about is how far it went from its starting point. If I confuse you more, sorry, just unwatch that in your brain. That's the whole lesson, I think, on acceleration. Super, super important. Do the practice problems and the homework, and we're going to become physics scholars. There was one important thing that I was going to say. I don't remember if it's this lesson or next lesson. Okay, it's this lesson right now. So let's do one last example, a conceptual example of acceleration. Let's say you get an elevator. You guys have ridden elevators before. If not, you probably know what they are. Let's say you live in a 9-story building. You get in the elevator on the ground floor, and then it goes up to the 9th floor. And elevators don't go that fast. I'm going to tell you guys the speed of the elevator. You guys think, while I write it in, no. What's the sign? You can enter one of these two questions. What's the sign of the elevator's acceleration? Or what direction does the elevator accelerate? Because acceleration is a vector also. They're actually the same question. So answer this question for me now. The elevator goes upward. It goes in the positive direction. Is the acceleration also upward? Is the acceleration also in the positive direction? Tell me right now. I'll tell you guys the speed of the elevator on every floor. You tell me, does the elevator accelerate upward, downward, or neither? This question doesn't really make sense until I give it the speed. So here's the floor. Here's the speed, or the velocity, in meters per second. Technically, it's the magnitude of velocity. Let's say you get in the elevator. How fast is the elevator moving when you get on it? Hopefully, 0 meters per second. You get off at the ninth floor. Hopefully it's not moving when you get off. But it can't just not move the whole time. So the elevator goes to 1 meter per second, 2 meters per second, 3 meters per second. Let's say it stays there for 3 floors and then drops back down. So I was just kidding when I asked you guys the first time. Now I'm really asking you, which way does the elevator accelerate? Tell me for real this time. Go. What do you think, Sage? The elevator accelerated upward because it went upward, obviously. Hmm, okay. What do you think, Hazel? The elevator didn't accelerate because it went from 0 to 0. So no acceleration. Hmm. Daisy? The elevator didn't Hazel said Daisy said the elevator had multiple accelerations. And that's true. To figure out acceleration, you have to look at change of velocity. The velocity changes in multiple ways. There's a lot of glare. But the elevator had the elevator went from 0 to 1 to 2 to 3 meters per second. So for this part of the motion, the acceleration was positive or upward. But then, elevators don't just speed up forever. There's definitely some time when the elevator is moving at a constant speed. If it's moving at a constant speed, it's not accelerating. The acceleration is 0. But at the end, you can't just like jump off the elevator when it gets to your floor and have it shoot past you. The elevator's got to stop too. So it decelerates back down in a negative acceleration. So the what your brain says, well, of course the elevator goes up, so it accelerates up. That's not true. You can't just jump to that conclusion. You have to think all the way back. What's the definition of acceleration?